All right, ladies and gentlemen, today we're going to be discussing the first topic of our new unit on atomic theory. We're going to be looking at a idea which has at least been presented to you in previous science classes, and you've probably heard something about this from just regular popular culture. Today we're going to be talking about radioactivity and radioactive decay. So we'll go ahead and get started here. There's a definition up on the board that defines radioactivity for you. We define radioactivity in this class as the spontaneous decay of unstable nuclei producing penetrating radiation, either in the form of particles or energy. Now that is a big mouthful of a definition. Let's go ahead and take a little bit of time to kind of break that down into a little bit simpler English language here. First off, radioactive decay is spontaneous. And if we think for a minute about what it means to be spontaneous, spontaneous means to be unpredictable, something that just happens. So radioactivity is a spontaneous process. It is unpredictable in nature. You can't really say when any one given atom will undergo a radioactive decay. The second term there is to decay. If you think about what it means to decay, we mean to break down or to break apart. And what are we breaking apart? We are breaking apart an unstable nucleus of an atom. Now recall the nucleus of the atom is the center part of the atom in which two types of subatomic particles are found, protons and neutrons. Now understanding why some nuclei are inherently unstable is a kind of big idea in terms of explaining radioactive decay. If you consider that the forces that exist within the nucleus that we're familiar with, it's really only a repulsive force that you guys currently understand. That's because within the nucleus of the atom, we've got protons which are positively charged, and we've got neutrons which are neutrally charged. Now, if you recall from your rules of attraction and repulsion between charged particles from your physics days, like charges repel, but opposite charges attract. So the force that exists between two adjacent protons is a repulsive force, which might lead us to believe that all nuclei are inherently unstable. But if that were the case, then it would seem that the nucleus of the atom would be something that would just shake itself to pieces, and there wouldn't be any atoms in our universe, which obviously isn't the case. So to explain actually what's holding together these nuclei, we need to have an understanding about one of the other fundamental forces of nature. In previous science classes, you've probably discussed two of the forces of nature in great detail. That is the electrostatic force, which is familiar to you guys, the electromagnetic force from your physics days, talking about the attraction between positive charges and negative charges. You're also probably very familiar with the force of gravity. That is an attractive force that exists between any massive objects within our universe. Now, as it turns out, there are other fundamental forces of nature. They just are kind of hidden from our day-to-day view, and so a lot of times we pretty much ignore their existence. But one of those fundamental forces of nature is what's referred to as the strong nuclear force. The strong nuclear force is an attractive force that exists between particles within the nucleus of the atom. Those are the protons and the neutrons. So what we really have at this point is kind of a balancing act, a tug-of-war, if you will, between the attractive force, which is holding together those protons and neutrons, and the repulsive force that is pushing those protons apart. Now, it would make logical sense to assume that if the attractive force is greater than the repulsive force, the nucleus would be more stable and hold together. But for some atoms, and if we think about on our periodic table, atoms that we have some familiarity with their inherent instability, when you think about radioactive decay, elements come to mind like uranium or plutonium. If you think about where those atoms are positioned on the periodic table, they're down towards the bottom of the periodic table, where you've got lots and lots and lots and lots of positive charges in that nucleus. And increasing the number of positive charges there in that nucleus increases the repulsive force pushing them apart. And therefore, at a certain point, we would expect that that nucleus itself would undergo a blast of radiation as it essentially blows itself apart, producing, in this case, what we refer to as penetrating radiation. That is the emission of particles or energy that are essentially ejected from the nucleus as the nucleus moves from a higher potential energy state, with those protons packed in close together, to a lower potential energy state. And that's really what we mean by radioactive decay. It's essentially the nucleus shaking itself to pieces because of its inherent instability. Now, as it turns out, there are many different things which can be ejected from a nucleus of an atom. And what we're going to be looking at next here is a table of radioactive decay particles that potentially could be ejected from an atom's nucleus. So you can take a moment right now and copy down the information on this table. You can go ahead and pause our recording at this point. Once you have copied down the table, let's stop for a minute and talk about each one of these different types of radioactive decay that can be emitted from the nucleus of an atom. So looking at those atoms again, if we consider an atom that's got lots and lots and lots of positively charged protons in the nucleus, as well as a number of neutral neutrons within that nucleus, if the repulsive forces between those protons are so great that the atom shakes itself to pieces, in essence ejecting some of those positive charges and thereby lowering that repulsive force, sometimes the particle which is ejected contains a total of 2 protons and 2 neutrons. So if we pull off those 2 protons and 2 neutrons, we call that particle an alpha particle. Now looking at the periodic table and recognizing that the ejected particle had a total of 2 protons, that would give that particle an atomic number of 2. And therefore we could say that this particle which has been ejected is really the nucleus of a helium atom. Again, 2 protons and 2 neutrons. Now recognize that this is only the nucleus of the helium atom. We haven't ejected any electrons at this point, which means now that this alpha particle, this helium nucleus, is a positively charged particle with a charge of +2. The symbol we give to this alpha particle is from our Greek alphabet here. It is the Greek letter alpha, which looks like a little fish. And the mass of an alpha particle, recalling that the mass number of a particle is the sum of the protons plus neutrons within that nucleus, we're going to go ahead and assign this mass number to be approximately 4 AMU, or atomic mass units. Now, moments from now, we are going to be looking at nuclear equation symbols here and how to balance nuclear equations. If you recall from some of our terminology when we were discussing isotopes earlier in the year, to write a nuclear equation symbol, we're going to start off with a symbol of this particle, which is a helium nucleus. In the upper left-hand corner, we put the mass number, which for this helium nucleus or alpha particle is a 4. And the lower left-hand corner, we're going to include the atomic number, again, which for helium is 2, in reference to the 2 protons that were ejected from that nucleus. Now, one of the things that we are interested in when discussing radiation is essentially the damaging effect of radiation on living systems. And as radiation absorbed in large quantities by living systems can lead to large amounts of damage to tissues and cells, something we're interested in as humans is protecting ourselves from that radiation. So one of the things we want to talk about on this paper here is really a discussion of how you can protect yourselves, and by that we mean the shielding necessary to keep this particle from causing damage to your body. Essentially what we can stop this radiation with. Now on the atomic level scale, it might seem like an alpha particle is a really, really small thing, just being 2 protons and 2 neutrons. But really in terms of the sizes of radiation that tend to be emitted, these alpha particles are pretty much huge. These are like atomic scale bowling balls. So you can imagine taking those bowling balls and shooting them at, say, like a net in a tennis court. The bowling balls probably aren't going to pass through. They're much, much larger than the size of the things that they tend to be hitting. Now, that being said, stopping an alpha particle is pretty easy to do. Pretty much anything will do the job. Paper blocks alpha particles. Your clothing definitely blocks alpha particles. But that being said, that doesn't mean that alpha radiation is not dangerous radiation. Again, going back to the analogy about the atomic scale bowling balls, yeah, the bowling ball might not fly through the net of the tennis court when you shoot it out of a cannon at it, but it certainly is going to damage the net. And There is very real damage that is caused by alpha radiation. As it turns out, many of the particles that are emitted within cigarette smoke contain alpha particle emitters. Things like polonium and lead are absorbed very, very well by tobacco plants and therefore find their way into smokers' lungs. And one of the reasons why smokers tend to develop large amounts of cancer, lung cancer in particular, is because once those particles of polonium or lead get lodged into their lungs, they just go blasting away with those alpha particles, leading to damage to those cells. All right, at this point we've discussed alpha particle radiation. The next type of particle is a kind of confusing one to consider in comparison to alpha particles for how it actually works. This is what we refer to as a beta particle. By definition, a beta particle is a high energy electron, which doesn't sound too confusing until you start to think about it for a little bit. So recall our definition of radiation was the spontaneous decay of unstable nuclei producing penetrating radiation. And you might be thinking to yourself, well, stop for a minute here. This is a nucleus which is decaying. How are we spitting out electrons? Because the electrons aren't found in the nucleus of an atom. The electrons are found around the outside of those atoms in those orbitals or shells. So where's this electron coming from? And to get to that idea, we're going to kind of hold off on the discussion for a little bit here, but I want to give you some symbols. The symbol for a beta particle emission is the Greek letter beta, which is just a B with a little bit longer tail. Recall from your previous experience, the mass of an electron in comparison to a proton or a neutron is very, very, very small. It's not zero. Electrons are mass, but we're going to go ahead and call it approximately 0 atomic mass units. Really, the true value of the mass of that beta particle is really about 1/1873, or 1 divided by 1873 of the mass of a proton or a neutron. Now, in writing the nuclear equation symbol of a beta decay, the mass of an electron, the mass number in the upper left-hand corner, is essentially 0, so we'll just go ahead and call that a 0. The symbol we're going to give it is just a lowercase e for electron. And the lower left-hand number there, the atomic number, recall the atomic number tells us the number of positively charged protons. Well, the electron is negatively charged, so we're going to go ahead and assign this atomic number of -1, referring to its negative charge. And last but not least, in terms of shielding from these beta particles, given the relative size of those beta particles in comparison to the alpha decay, they're very, very, very small, and as such, it is harder to block this radiation. In general, to block beta decay, depending upon the energy of those electrons emitted, a couple centimeters of plastic shielding generally does the job. Water, a centimeter or so of water, is also in general sufficient to block beta particle decay. But that being said, less dense materials or things like paper and clothing, those probably aren't sufficient to actually block all of that beta radiation, and so much of it will actually pass through. Now let's get back to that idea of where this beta particle decay is actually coming from. Recall that we said the nucleus is what is breaking apart in a beta emission. Now in general, if there's too many positively charged protons in the nucleus, we're going to end up seeing an alpha particle decay, spitting out some of that positive charge and therefore lowering the potential energy of the nucleus. The opposite is true in a beta decay. In a beta decay, we actually have too many neutrons in general. And as such, we would expect to see not a positive charge emitted, but a negative charge emitted. And here's the kind of big idea. In a beta decay, we're going to go ahead and look at the nucleus itself spitting out an electron. If a negatively charged electron is removed from that nucleus, whatever remains behind is going to be more positively charged. I'm going to kind of leave us on that idea for just a moment here until we get to balancing our nuclear equations to explain exactly how weird that beta decay actually is. And moving on to our next type of radiation. The next type of radiation is one that you are probably familiar with from your physics days, those of you who looked at that spectrum of electromagnetic radiation. Gamma radiation is part of that electromagnetic spectrum. And so essentially gamma radiation it's light. It's a very high energy, very, very high energy electromagnetic radiation. So it's essentially just a very, very, very high frequency photon or particle of electromagnetic radiation or light. The Greek letter gamma that we'll use for symbol here kind of looks like a Y with a kind of bit of a squiggly tail there. Now, given that this is essentially electromagnetic radiation, it's light, we have zero mass in this case. In writing a nuclear equation symbol, we're going to go ahead and give this a big capital E. The charge and atomic number of just radiation, light radiation, is 0, so we'll give it a 0 and a 0, both for the atomic number and the mass number. Sometimes you'll actually see it just written as an up arrow showing radiation emitted. Now again, shielding from this gamma radiation is a very, very difficult thing to do because it's incredibly high energy. If you think about other high energy radiation, you know how hard it is to block. If you remember going to your dentist to get some x-rays done, recall that they put on a lead vest on you, and then the little dental assistant there runs and hides behind a wall, generally a concrete wall, before they turn on the x-ray machine. X-ray radiation is actually lower energy than gamma radiation. So in general, to block these high energy gamma rays, you need several centimeters, not of plastic, but of lead, or feet of concrete. So again, very, very high energy damaging radiation. The last two particles on here are familiar particles. These are the proton and the neutron. Description, pretty straightforward. You're already familiar with protons. What do we know about them? Protons are positively charged. So we're going to go and define a proton as the positively charged particle within the nucleus. The symbol for a proton is going to be a P. The mass of a proton is approximately 1 atomic mass unit, or 1 AMU. And again, I say approximately. We'll discuss that momentarily here. The nuclear equation symbol that we use to describe a proton, well, if we think about it here, the atomic number of a proton, that is the number of protons in a proton, again, obviously is 1. The mass number, also 1. And you'll see this written because it's got a single proton. Atomic number 1 in your periodic table is a hydrogen nucleus there. You might also see it written as 1, 1 with a little p there designating a proton. Shielding protons is generally about the same as shielding from alpha radiation. They're both positively charged, they're both relatively small, so because they're charged, they are attracted to other charged objects. They get blocked relatively easily, especially in comparison to our next one, the neutron. Whereas the proton was the positively charged particle in the nucleus, the neutron is the neutral particle in the nucleus. Symbol for neutron, not surprisingly, is an N. And again, the atomic mass of a neutron is approximately, again, 1 AMU. It's actually slightly more massive than a proton, for reasons, again, we'll discuss momentarily here. And in the nuclear equation, the mass number of a neutron is 1. The atomic number, that is the total charge in the of a neutron, is 0. It is neutral. And the symbol, again, is an N. Shielding for neutron radiation is a very, very important consideration because, as it turns out, neutrons are the particles within a nuclear reaction that are actually the self-sustaining portion of that nuclear reaction is dependent upon the number of neutrons present in that reaction. We'll be seeing that a little bit later when we talk about nuclear equations. So if you actually have a nuclear reactor, you want to shield some of that reactor from the surrounding environment as well as from itself, for reasons we'll talk about momentarily. So shielding neutrons is very, very important. It's also very, very difficult to do. Neutrons, being neutral, tend to pass through things more easily than the positively charged alpha particles and protons that get attracted to other charges, and therefore they're more difficult to block. In general, we use a couple of different elements to block neutrons. The big ones are either boron or cadmium, as it turns out. Those are found within reactor cores. And we'll talk about how those work a little bit later in our unit when we discuss how a nuclear reactor core actually functions. So those are the 5 types of radiation that we're going to be focusing on in this class. There are other types of radiation that are emitted that are more exotic than ones we have listed, but for the time being, we'll kind of focus on these. So now that we have an idea about what types of things can be emitted from the nucleus of an atom during a nuclear decay, we're going to move on next to how we can actually show this nuclear decay through a little bit of chemistry and balancing a nuclear equation. Recall from your previous science classes that the reason why we must balance equations is that there is a law you are all familiar with called the law of conservation of matter, which says throughout any process in our universe, the amount of stuff in our universe remains relatively constant. Now, essentially, that conservation of matter is just a subset of a greater, more meaningful law, which is called the law of conservation of energy, which says, in essence, energy and charge are conserved in any process, whether it's a chemical process or a nuclear process. So these equations are subject to the same laws that govern all regular chemical reactions. Now what that means in terms of a balancing chemical equation is that you've got to have the same number of atoms of both things on both sides of the equation. That is, you cannot just create atoms of carbon out of nowhere. The weird thing about a nuclear reaction is that, as it turns out, you can change one element into another. Because remember, if we're messing around with the nucleus of these atoms, we're changing the number of protons, we can actually change the atomic numbers of these particles, which means that essentially we're going to be accomplishing what the alchemists were trying to do years and years ago, trying to change one thing into another. But laws of conservation must still be upheld, which essentially means in these nuclear equations, mass is conserved. That is, the sum of the mass numbers on both sides of our equation have to be equal to each other. And at the same time, charge is conserved, which essentially means now that the atomic number, the number of protons on both sides of the equation, must be conserved as well. So we'll go ahead and look at a couple of examples of nuclear equations here. The first equation is showing the nuclear decay of americium-241, which is an isotope of element number 95, looking on your periodic table. If you do not already have your periodic table out, you should have it out right now so you can follow along. So looking at that species here, americium-241, we're going to go ahead and assign its atomic number, as we said, 95. And it seems that the species being emitted by this radioactive particle is a helium nucleus, which means we're really looking here at alpha particle decay. So we are ejecting a particle made up of 2 protons and 2 neutrons. And we want to figure out what we are left with when that ejection occurs. Now, reasonably thinking here, if we've got a big americium nucleus made up of a bunch of protons and a bunch of neutrons, and we'll go ahead and color in those protons here. And a particle made up of 2 of those protons and 2 of those neutrons gets ejected, essentially what's left over is just the remaining chunk. So essentially we're looking here for what's left. So applying our law of conservation of matter, we know we started off with a sum of the mass present of 241 AMU. The particle ejected had a mass of 4. So what must therefore remain, that remaining chunk of the nucleus, we call this the daughter nuclide, that remaining chunk should have a mass of 237, such that the sum of the chunk which was ejected, the 4 helium, and then the 237 AMU which remain, gives us the total of 241 that we started with. So mass has been conserved. By the same logic, charge is conserved. In the nucleus of that original americium atom, there were 95 protons. A chunk with 2 protons was ejected. That would leave us with the remaining 93 protons left over. So whatever this daughter nuclide is, it must have 93 protons. And looking up at your periodic table of the elements, we discover that the element with 93 protons, with an atomic number of 93, is the element Np, which is neptunium. Not surprisingly, the element between uranium and plutonium. So that's an alpha particle decay. Pretty straightforward here to understand how that decay works and how it shows conservation of matter. We are seeing the sum of the mass numbers remains constant at 241. The sum of the atomic numbers remains constant at 95, both before and after the decay occurs. Let's look next at this decay of an isotope of potassium. That is potassium 42. Find again on your periodic table potassium is element number 19. So we can fill in its atomic number, 19. And now check the particle which has been ejected. This particle ejected appears to be an electron. So this represents beta emission. That electron has a charge of -1, so we can put in its atomic number there. Now here's where stuff gets a little weird. Mass makes perfect sense here. We started with a particle with 42 protons plus neutrons, that is a mass number of 42. The ejected particle essentially had no mass, which means what remains still must have a mass of 42. Considering the atomic number, we started off with a total positive charge of plus 19. The particle emitted had a charge of -1. To conserve charge, that tells us that my new particle's charge must have a charge of 20, such that the sum of the particle, the daughter nuclei there, of 20, plus the -1 from the particle which was ejected, still equals the total of 19 positive charges that we started with. So again, here we've shown both matter has been conserved, mass, and charge has been conserved. Looking again at our periodic tables, we find element number 20. Element number 20 on your periodic table tells me that this new daughter nuclide is an isotope of calcium. Now stop for a moment to think just how weird this actually is. We've changed an isotope of potassium into an isotope of calcium by ejecting an electron from the nucleus, where there really aren't any electrons to begin with. So how did that actually occur? Well, we can kind of consider what's happening here if we look a little bit more in depth at a beta decay. We started off with 42 total particles within the nucleus. The total number of particles in the nucleus hasn't changed. What has changed is the charge. So if I started off with 19 total positive charges and I ended up with 20, the only way for that to have occurred would be if one of the things that originally didn't have a charge got rid of an electron. And recall, what originally didn't have a charge were the neutrons in the nucleus. So in essence, what occurs in a beta particle decay is that a neutron, a neutral particle, splits out a negatively charged particle, and what remains behind, if you subtract a negative from a neutral thing, is a positive. A beta decay really turns a neutron into a proton by ejecting an electron. And that is how we see an increase in atomic number while seeing no change in mass number. Again, a very weird situation. Now, one other weird situation here. I talked to you earlier about the mass of a proton or a neutron being approximately equal to 1 AMU, but I said, as it turns out, the neutron is a tiny, tiny bit more massive. Well, just how much more massive is it? As it turns out, the neutron is about a factor of 1/1873rd more massive than a proton. That is exactly the amount more massive than a proton, which is equivalent to the mass of 1 electron. All right, so we've seen here now how to write a couple of examples of radioactive decay. That is when one nucleus spontaneously splits apart, spitting out a particle. The other type of problem I want you to be familiar with and able to complete is now what we refer to as a collision problem. A lot of times when you're looking down at that very bottom of the periodic table where we're looking at all those weird exotic elements that are synthetically created, those are the elements, if you recall from earlier in discussion of the periodic table, do not have the font filled in on the periodic table, the elements like plutonium, americium, curium down at the very bottom there. Those synthetically created elements, most of them have been created using a device called a particle accelerator, which is a device that we essentially use to speed up particles to pretty impressive fractions of the speed of light and then smash them together. And essentially what you end up with is an atomic scale train wreck. You aim a atom at a particular chunk of matter and then you just smash it together and see what's left over. So these particle collision problems have to obey the same laws of all the other ones. We still are obeying conservation of matter. But now than just having one thing break apart, instead we're having two things smashing together and figuring out what the remains must be. So we'll go ahead and look at an example of this collision problem here. The very first one is an example of the collision of lithium-6 with a neutron. So to start off, let's go ahead and just fill in the information we currently know about these species. Find lithium on your periodic table. It is in the upper left-hand corner. The atomic number of a lithium atom is 3, so we can fill that in. And the particle we're smashing into it appears to be a neutron. Neutrons have an atomic number of 0 due to their neutral charge. And when that collision occurs, it appears we are forming the nucleus of a helium atom. That is, we're giving off an alpha particle. And really the key here is now we've got to figure out what else remains, what else is left over. So essentially to solve this problem, we're just going to compare what we started with, to the left of that line, with what we ended with to the right. And we need to make sure that the amount of matter and charge is equivalent on both sides of this reaction. So starting off with mass, if you look on the left-hand side, the lithium atom had a mass of 6 AMU, and we smacked into it a neutron with a mass of 1, meaning the total mass here on the left-hand side was 7. Matter is conserved, so on the right-hand side, the helium nucleus has a mass of 4. To conserve that same total amount of mass of 7, we need to therefore have a particle ejected which has a mass now of 3. The 4 plus 3 on the product side is equivalent to the 6 plus 1 on the reactant side. Same thing must be true for the atomic number, that is the charge. On the left-hand side, the lithium atom has a total positive charge of plus 3. The neutron has 0 positive charge, so the sum is plus 3. On the right-hand side, we've got a helium nucleus with a charge of plus 2. To conserve that charge, that means whatever this other particle is, it's got to have a charge of plus 1, so that we maintain that same positive 3 overall charge on both sides. And now defining what this is we've actually made, looking again in your periodic table, we've got an element with an atomic number of 1. That's a familiar element. This is an isotope of hydrogen. It is a heavy isotope of hydrogen, which has got a couple of extra neutrons. We call this isotope tritium. And again, we've conserved both mass and charge in balancing that nuclear equation. All right, we'll do one more example here. Have a look at the bottom problem here. This is a big atom down at the bottom here. This is an isotope of Einsteinium, Einsteinium-252. Look to the very bottom of your periodic tables. Einsteinium is in the actinide series of those intertransition metals. It is element number 99. So with this Einsteinium-252, we're smacking some mystery particle into it. And we're telling you this time what the products of that collision are. We've got a new isotope here, which is an isotope of lawrencium, element number 103 on your periodic table. And then 3 neutrons are emitted. Recall each of those neutrons has a mass of 1 and a charge of 0. So to figure out what this mystery particle that must have hit the Einsteinium is, we're again going to go about balancing both matter and charge. We'll start with matter to begin with here. On the left-hand side, the Einsteinium isotope has a mass number of 252. On the right-hand side, the lawrencium has a mass number of 258, and we've got 3 neutrons, each with a mass of 1, so that's a total of 261. So to get from 252 on the reactant side to 261 on the product side, that is a total mass of 9 that needs to be accounted for. So 252 plus 9 gets us to 261. Just the same way 258 plus 3 times 1 gets us to the same 261. Now in terms of the atomic number, on the right-hand side of our equation, our total atomic number appears to be 103. That is the total positive charge in the system. On the left-hand side, we've got 99 for Einsteinium. So to get up to 103 on both sides, that means that whatever this particle is must have an atomic number of 4. So 99 plus 4 gives me the same 103 that we ended with. And last but not least, we can now figure out what element we must have smacked into our Einsteinium now. If we've got an atomic number of 4, looking on your periodic tables, this must therefore be an isotope of element 4, which is beryllium. So again, we have balanced both matter and charge, and we therefore have shown that the law of conservation still applies within these nuclear equations.